Deadlock avoidance. As I told you, dear student, the system will try to keep this operating system in a safe state, and they will not let the system to come to go to the or to go into the unsafe state. But how this will work, let's try to understand. Dear student, the deadlock avoidance method require that a system must have a prior database or a prior information about all available resources. The system must have what? The system must have a prior information or a prior database, okay, about resources and about their available states, okay. So this will give a kind of smartness to the system that whenever processes are going to request particular resource in the particular amount, then the system will have a prior database. The system will compare their request with their database. That is, the system can satisfy the request or not. If the system can satisfy the request, so how much? How much resource can be allocated? Is the full request can be satisfied or partially can be satisfied? Okay, because this database will give capability to the system to take a fair decision. You know that if a system don't have a database, then the system cannot decide that how much resources are available with the system and how much are free and how much is going to be free. Okay, the system will have no idea about this, and that's why the system will not able to fairly deal those processes who are requesting resources. So simplest and most useful model requires that each process declare the maximum number of resources of each type that it may need. It may, dear students, for example, I have a process. Let's suppose this is our system. Okay, and the system have a database. The system have a database of all resources. For example, resource R1, resource R2, okay? This much instance are free. For example, they have information about the instance, okay? Or for example, 2, 3, etc. So let's suppose there is another process. The process is going to be executed. So according to the rule, this process must declare that how much resources will be required by the process. Okay, must declare the maximum amount of resources. The maximum amount of resources, or you can say the maximum amount of instance of a particular resource. Okay, they must declare that. Let's suppose they declare that I need 5 instances of R1. Now the system will compare this request with this available database. Remember, if the system do not declare, then it means that the operating system cannot deal with this process. Okay, the process must declare. This is the first principle. Dear students, we will try to understand today's lecture in a very sequential fashion, because we will have discussion about banker algorithm, so it will be very difficult to draw all the required concepts in one time. Okay, so that's why you have to try to understand it step by step. Like I told you, one principle, you should note this with yourself, that each process must declare maximum number of resources. You must write this with yourself, because it's a principle in the deadlock avoidance that each and every process must declare the maximum number of. Declare doesn't mean request. Okay, declare means they have to specify that much resources will be required. The deadlock avoidance algorithm dynamically examines the resource allocation state. In the deadlock avoidance method, in the system, deadlock avoidance algorithms will be running. In each and every time, they will examine the system. Is the system in the safe state or not? okay? And they will try to keep the system in the safe state to ensure that there can never be a circular weight, because if you remember, the circular weight was one of the major cause of deadlock. That's why the deadlock avoidance algorithm will each and every time check that is there any waiting process, or is there any process who is holding some of the resources and waiting for some other processes to create a circular weight or not. So the conclusion of the second paragraph is that the deadlock avoidance algorithm will dynamically examine the system each and every time. And the first paragraph conclusion was that the process must declare the maximum number of required resources. The second one, resource allocation state. As I told you before that the system have a prior database about resources, about available resources in their states. So now the state will be defined based on what? The state will be defined based on what? And okay, and also we can say that, focus here, resource allocation state is defined by the number of available and allocated resources. How much resources are having by the system will be listed in the available resources, but how much are available? Available mean free resources, okay? Remember, available mean free resources. Free resources mean resources which can be allocated by the system to a new arrived process. Allocated resources mean those resources which are already holding by the running processes, okay? And maximum demands. The maximum demand mean the need amount of resource. Like for example, in our example, the previous example was, let me take another example. For example, the system have R1 and R1 3 instances, but the P1 is demanding 5 instances. So of course, the system will allocate maybe 1 or maybe 2 or maybe 3 of these instances, okay? It will be decided by the system. So let's suppose the 3 instances are allocated to the P1, but where the demand is how much? 5. So we can say that the need amount will be how much? 5 minus 3 is equal to 2. So such type of information the system must have. So dear students, now come back to this first, that the system must have available resources information beside their states. Now in the state will be what? Available resources mean free resources, allocated resources, and the maximum demand, or you can say the need amount of resources. This last word, the maximum demand, came true in 2 cases, okay guys? The first case which has explained that the need, and the second case can be this 5. This can be the maximum demand and this can be the need, okay? Both come true under this last maximum demand terminology. And in the next coming slides, we will use both, okay? But when you want to go narrow, then this will be specifically specified by the need, and this will be specifically specified by the demand, just demand, okay? Okay, guys. As I told you before, that the system will try to, our deadlock avoidance algorithms will try to keep the system in the safe state. So what is safe state? Let's try to understand the safe state. I will first start from the second definition. A state is a safe. A state of what? A state of the system will be considered a safe state if the system can allocate all resources requested by all processes. You know, in our system, there will be multiple resources and multiple processes will be running. But when the system can allocate resources to those running processes, how much is demand, okay, by the processes? without entering a deadlock state, then we will say that the system is in a safe state. See, dear students, when the system has sufficient amount of resources and they can satisfy the request of processes without facing lack of resources or without facing no resources, then we will say that the system is in a safe state. Why? Because I told you that when the system has sufficient amount of resources. Clear? So now the second definition. When a process requests an available resource, available mean, of course, when the process is arrived, they will request the free available resources. The system must decide if immediate allocation of that resources leave the system in a safe state or not. It means that if the system allocate those resources immediately, so then what will be the system state? When the system will face lack of resources or not lack of resources. If the system is facing lack of resources, that means the system will be not in the safe state. But when the system is facing not lack of resources, it means that the system is in a safe state. So conclusion is that in both cases, when the system have sufficient amount of resources, when the system have sufficient amount of resources and they can satisfy the request of processes, our system will remain in a safe state. But if the system don't have sufficient amount of resources, then it is possible our system will go to the deadlock state. Okay. So like for example, let's take our previous example, the bank example. We have 3 cashier. Let's take 2 cashier to make it easy. We have 2 cashier. Let's suppose in the whole bank, and there are multiple customers. There are multiple, 3 customers. And these 3 customers are demanding multiple amount of money. For example, this is demand 150K, this is demand 200K, and this is demand, for example, 1 million. So they are demanding for this much amount for the withdrawal, and here the system, the bank will see that if the bank allocate or satisfy the request of 150, the request of 200K, and the request of 1 million K, what will be the bank state? If the bank will face no lack of money, that means the bank is in a safe state. Bank can deal the 4th and the 5th customer because bank has sufficient amount and the bank can satisfy the request, no problem. The bank will not face lack of money. So dear students, in such cases, the bank will be in a safe state. In such case, our system will be also in a safe state because of sufficient amount of resources. Okay, dear students, let's take an example to understand that is the system is in a safe state or not. System is in safe state if there exists a sequence of all the processes. Okay, the sequence of what? Like for example, I have P1, I have P2, P3. This Pn mean number of processes. Okay, it can be P4, P5, 8. But I will take just 3 of them. P3. Okay, in the system, such that for each Pi, remember Pi mean a running process. Pi mean running process. And here P1, P2, P3, all of them can be running process. Okay. In order to take it simple, we will use Pi. We will not use P1, P2, P3 each and every time repeatedly. Okay. So such that for each Pi, the resource that Pi can still request can be satisfied by currently available resources. Okay. So let's suppose the P1 is demanding 5 resource. It's demanding 3 resource. It's demanding 10 resource. The system allocate to this 2 resource, 2 resource, and 5 resource. So how much resources are allocated? Allocated resources is equal to 9. Clear? Demanded resources is equal to what? 5, 3 is equal to 8, 8 plus 10 is equal to 18. Okay. So how much is required? We have to minus them, but we will not do them right now. Let's make it easy because we will study them in the banker algorithm. So there is the current condition that the allocated resources is equal to 9. The demand resource is equal to 18. Clear? Let's suppose the system still have more available resources. Let me take it F resources. F resources mean free resources. For example, 3 resources are free with the system. 3 resources are free with the system. Now come back to this again. Such that for each PI, the resource that PI can still request can be satisfied by currently available resources. So dear students, this is currently available resources, which is 3, plus resource held by all the PJ with, okay, just to this point. We know this, dear students, that right now the system have 3 free resources, where the P1 is demanding how much? 5, 2 is already allocated. So how much is need by the P1? The P1 need, okay, the allocated minus maximum demand is equal to 3, okay, because 5 minus 2 is equal to 3. So the system will allocate these resources to who? To P1. So it means that P1 will have their sufficient amount of resources and P1 will be finished. When the P1 will finish, the P1 will release this 2 instance and this 3 instance. Now the system will have more resources. So the 2 instance was already allocated and they were using, the 3 were newly allocated. So this 2 will be released. 3 plus 2 is equal to 5. So now the system has how much resources? 5 resources. That's why I told you here, resources held by all the PJ. It means that the held resources, the held means the occupied resources will be released when the process is finished. So collectively, when the system will have back those resources and when the system will add them with the available resources, after that, if the system can satisfy the request of P2 or P5, then it means the system is in a safe state. The system is in a safe state. I know this example is a little bit complicated, but no problem. If you understand this even 30%, so it will be very okay, because such type of examples we will solve practically in our coming slides in the banker algorithm, okay? So dear students, now come to this with J smaller than I. J mean what? J mean the need resources is smaller than the I. Like for example here, the P3 demand 10, available allocated 5, required how much? 5 is required and the system have 5. So it means this is equal to 5. So it means the system can satisfy this request. Even the system can satisfy the request of P2 because P2 require 1 more instance. In this example, our system isn't fully in the safe state. Our system is fully in the safe state. Okay. There is also the explanation of the same example in this area. You can see if PI means running resource, running process. If PI resource needs are not immediately available, then PI can wait. Have finished, just like P1 was waiting, because P1 demand 5 resources, the system allocate them 3 resources. Actually, he was waiting for more resources, and also the P2 and P3. But remember, that way doesn't mean that they will always wait for more resources. The system had sufficient amount of resources, okay? That's why there was no deadlock. when PJ is finished, when the PJ, a process which is running and already holding some resources, is finished, PI can obtain needed resources. Then the waiting PI can obtain their all amount of resources because the PJ will release their resource. So they will execute the resource and they will return allocated resource in, and they will be terminated. Who will be terminated? PI will be terminated because PI was waiting to have the full resources. When the full resources become available with the system allocate them. Now the PI execute those resources, and after termination, the PI return those resources to the system. So dear students, when PI terminates, it means PI state will become true. Their termination will become true. It will not wait until they become true, okay? So their termination will become true, so PI plus 1. So then PI plus 1 mean that the PI will release their resources and their resources will be added with the free available resources in the system. So dear students, if such cases occur, it means our system is in a safe state because our system is not facing lack of resources. Basic facts. Okay, what is unsafe state? Dear students, unsafe state mean when there is possibility of deadlock. And how the possibility of deadlock will be there? When the system don't have sufficient amount of resources. Just like I give you the example of bank. The bank have, for example, the bank have 1 million Afghani, and the demand is this 3 customers are demanding 1 million. So now, if the bank satisfy the request of just this customer, then the bank will be in an unsafe state because these 2 customers will wait and the bank will not have sufficient amount of resources. And this is called what? That the system is in an unsafe state and there is possibility of what? Deadlock. Why possibility? Because maybe another customer will come and they will deposit some of their amount, but it's maybe, okay? Otherwise, right now the bank is in a what? The bank is in an unsafe state. So dear students, whenever the system don't have sufficient amount of resources, then there is possibility of what? And there will be in the unsafe state and there is possibility of deadlock. So now come to the basic facts. If a system is in a safe state, then there is no deadlock. Why? System has sufficient resources. If a system is in an unsafe state, there is possibility of deadlock. Why? Because of the lack of resources, the system was in unsafe state. And that's why there is possibility of deadlock. Avoidance algorithm will ensure that the system will never enter in the unsafe state. So how? Because they will try to fairly allocate the resource. Let me give you the example with in the same diagram. The bank manager is using, let's suppose the bank manager is using banker algorithm. So the bank manager will say this customer A that right now we will give you 2 lakh Afghani. We will give you 2 lakh Afghani and you have to wait for 4 more minutes, or you should come after a few minutes or after a particular amount of time because we cannot satisfy your complete request. So we will give you some amount and you can use them. And same to this. So see, if the bank manager give them 200K, it means the system will still have 400K with their self. System remain in a safe state. It is possible that a customer 4 will come and they will deposit 2 million Afghani. So then the bank manager will say, yes, you guys can come and you guys can have your full amount of money. So this is called what? Fairly allocation of resources. And that such things will be done by the deadlock avoidance algorithm. And the deadlock avoidance method. So this was the basic fact. If the system is in a safe state, no deadlock. If the system is in an unsafe state, possibility of deadlock. And the avoidance algorithm will try to keep the system in a safe state and will not let the system to enter in a unsafe state. Okay. So safe state, no deadlock. Unsafe state, possibility of deadlock. Okay. There's possibility of deadlock, there's no deadlock.